Let's prove one of the most important inequalities in mathematics, the Cauchy Schwarz Inequality. This says that suppose x and y are in Rd, so they are d-dimensional vectors. So maybe x looks like a vector with components x1, x2, all the way up to component xd, right? It's a d-dimensional vector, it's in Rd, and y is going to have this same kind of structure. Then the Cauchy Schwarz inequality holds, which says that the magnitude of x dotted with y is going to be less than or equal to the magnitude of x times the magnitude of y. We're first going to start with a trivial case, which just means that it is very clearly true just by observation. So if x was to be equal to 0, or if y was to be equal to 0, or if both these things were true, then clearly our Cauchy Schwarz inequality holds. This is a trivial case. So we are only going to consider the case when x is not equal to 0 and y is also not equal to 0. Now the way we're going to proceed is actually by proving something a little bit easier. So we are going to focus on proving that x dotted with y is less than or equal to the magnitude of x times the magnitude of y. So this is going to be the bulk of our proof, and then once we have this, it's really easy to generalize from here to our original Cauchy Schwarz inequality. A classic strategy for proving inequalities is to take a non-negative quantity and just do some careful manipulations with that. So we're going to fix epsilon greater than 0 and make a really clever observation that's going to lead us to what we want. So this is clearly a non-negative quantity, right? This is going to be a positive number squared, so this is clearly going to be greater than or equal to 0. And if we were to expand that out, just using our FOIL, right, first, outer, inner, last, we're going to get that this is actually equal to epsilon squared times the magnitude of x squared minus 2 times the dot product of x and y plus the magnitude of y squared all over epsilon squared. And what we can do now that's going to push us a step further is kind of look at our left side and our right side. So we have right now that 0 is less than or equal to our expanded form right here. What I'm going to do is add our 2xy to both sides, and this is going to give us this inequality. Our next step is to try and make this inequality as tight as possible, which means we want to minimize what we have on our right side while still holding this true. So when is this going to be minimized while still holding this inequality true? Well, that's going to happen when this quantity is exactly equal to this quantity. So let's do some scratch work on the side and see what value of epsilon is going to make that happen. And it just takes a little bit of algebra to solve for that epsilon. Now that we have our epsilon, let's declare this as our epsilon in our proof and plug that epsilon into our right side to see where that brings us. There you go. Now looking at our leftmost side and our rightmost side, we now have that 2 times x dotted with y is going to be less than or equal to 2 times the magnitude of x times the magnitude of y. That looks very similar to what we're trying to prove. All we got to do is divide by 2 on both sides to get that. Now our goal is to generalize this to be that original Cauchy Schwarz, right, that has the absolute value. So the way we can do this is breaking this up into 2 cases, right? We've already covered the 0 case, but this left side could be positive and it could be negative. So if x dotted with y is positive greater than 0, then this is pretty easy, right? We know that the magnitude of x dotted with y is going to be exactly equal to x dotted with y, and we know that x dotted with y is less than or equal to that right side, and so we've got Cauchy Schwarz in that case. Next, we're going to do the case where x dotted with y is less than 0. So in this case, we're going to first make an observation that the magnitude of x dotted with y is going to be exactly equal to negative x dotted with y, right? Because this is already a negative quantity. So if we say negative this, it's going to be positive, right? So that's going to have the same value on both sides. Then we're going to apply the inequality that we got earlier, right? So we're going to say that this right here is our first component and this right here is our second component applied here. So we'll have that negative x dotted with y is going to be less than or equal to the magnitude of negative x times the magnitude of y, which is just the magnitude of x times the magnitude of y. And what is negative xy equal to? That right there. So according to this equivalence that we have earlier, this is equal to that, and we have Cauchy Schwarz in the case when x dotted with y is less than 0. Now for the best part of the proof, I'm going to write my little QED and call that good.